Question 29. Number A is asking an electron is in F orbital. For F orbital, what possible values of the quantum numbers N, L, M, and S can it have? The answer with 4F electron, it means that N is equal to 4. L can have values either 0, 1, 2, or 3. L varies from 0 to N minus 1. 4 minus 1 is 3. It can vary from 0, 1, 2, and 3. For each value of N, we determine the value of M to see whether we can have the set of quantum numbers in which an electron is located in 4F orbital. For L is equal to 0, M is equal to 0. In that case, we have S. We have 4S. We don't have the 4F. For L is equal to 1, M is equal to minus 1, 0, and 1. Then, in this case, we are having 3 orbitals. P is the one having 3 orbitals. We have 4P. We don't have 4F. For A is equal to 2, we have M is equal to minus 2, minus 1, 0, 1, and 2. So how many orbitals do we have? We have 5 orbitals. D is the one which has 5 orbitals. Then in that case we have 4D. 4D because we have N is equal to 4. For L is equal to 3, M is equal to minus 3, minus 2, minus 1, 0, 1, 2, and 3. So this means that we have how many orbitals? We have 7 orbitals. F is the one which has 7 orbitals. So meaning that an electron in 4F, it is having L is equal to 3. L is equal to 3, M is equal to minus 3, minus 2, minus 1, 0, 1, 2, 3. In that case, you have 4F electron. This is where electron is located. Then our answer in red, possible values for the quantum number for an electron located in 4F. So it means we have N is equal to 4, L is equal to 3, M is equal to minus 3, minus 2, minus 1, 0, 1, 2, 3, and S, which is the spin quantum number, it will be equal either plus 1 over half or minus 1 over 2. The sub-question B is asking what is designation is given to an orbital having N is equal to 2, L is equal to 1, N is equal to 3, L is equal to 0, N is equal to 5, L is equal to 3, N is equal to 4, L is equal to 2. We move to the answer. For N is equal to 2, L is equal to 1. Then to find the designation of the orbital, we need to find M. M for L is equal to 1, remember M will vary from minus L to plus L. So this means that for L is equal to 1, we have M is equal to minus 1, 0, and 1. We have 3 orbitals. Then P is the one which has 3 orbitals. In that case, we have P, but because N is equal to 2, the designation will be 2P. For N is equal to 3, L is equal to 0, then M is equal automatically 0. In that case, we have 1 orbital. S is the one which has 1 orbital, but because N is equal to 3, we will have 3S. For N is equal to 5, L is equal to 3, M will be equal to minus 3, minus 2, minus 1, 0, 1, 2, and 3. How many orbitals? We have 7 orbitals. F is the one which has 7 orbitals. But because we have N is equal to 5, in that case we have 5F. For N is equal to 4, L is equal to 2, we determine M. M will be equal to minus 2, minus 1, 0, 1, and 2. How many orbitals? 5 orbitals. D is the one which has 5 orbitals. In that case, we have 4D because n is equal to 4. Moving to number C of this question, which of the following sets of quantum numbers are not permitted? So you need to check in these given quantum numbers, which one are not permitted or which one are not allowed. For n is equal to 2, L is equal to 2. Remember, L vary from 0 to n minus 1. Then n minus 1, it means 2 minus 1. L cannot be equal to 2. It can be either 0 or 1, but cannot be equal to 2. N cannot be equal to L. Then go to second, n is equal to 2, L is equal to 1. It's possible, yes. When n is equal to 2, L can vary from 0 to 1, because 2 minus 1 is 1. Means that L can vary from 0 and 1. Then m can be either minus 1, 0 and 1. So this is also possible. M is also, n of minus 1 is possible. What about s? S could be also either plus of half or minus 1 over half. Then this one is permitted. Going to the third one, n is equal to 2, L is equal to 0. Yes, it's possible that when n is equal to 2, L can be either 0 or 1. L is possible. Then m is also possible. When L is equal to 0, m also is equal to 0. It's also possible. But s is equal to 0. It's not possible. It's not possible to have the spin of 0. Because the spin quantum number is either plus 1 over 2 or minus 1 over 1 over 2. So this is not permitted. For the last one, n is equal to 2, L is equal to 1. Yes, it's possible to have L is equal to 1 when you have n is equal to 2. M is equal to 2. Is it possible? No. Then for L is equal to 1, M should be equal to minus 1, 0 and plus 1. So this is not permitted. M cannot be equal to 2 if L is 1. Let's continue to D. Explain if it is possible to have 1p2. So we need to check if it is possible to have 1p2. This is not possible because having 1p2, it means n is equal to 1. If n is equal to 1, L is equal to 0. M is equal to 0. We have only one s orbital. There is no way you can have p orbital. Then going to 2d5, n is equal to 2, L is equal to 0 or 1. Because if n is equal to 2, L should be either 0 or 1. Then if L is equal to 0, we have m is equal to 0, we have 2s. For L is equal to 1, we have m which will vary from minus 1, 0 and 1. We have 3 orbital, means we have p orbital, we have 2p. So then there is no way you can have 2d. For the last one, so here also it is not possible to have a 2d5. For the last one, to have a 3f, it's not possible. For n is equal to 3, L vary from either 0, 1 and 2. It cannot be equal to 3. It should be either 0, 1 or 2. Then for L is equal to 0, m is equal to 0. In that case, we have s. Then for L is equal to 1, m is equal to minus 1, 0 and 1. So 3 orbital. P is the one which has 3 orbital. In that case, we have p orbital. Then for L is equal to 2, m is equal to minus 2, minus 1, 0, 1 and 2. So how many orbitals? We have 5 orbitals. D is the one which has 5 orbitals. Then there is no you can have a 3f. If we are having 3f, we have up to the d orbital. We don't have the, for n is equal to 3, we have up to d orbital, not f orbital. This is also not possible, meaning that all of these equations, they are not possible. Not possible to have a 1p2, not possible to have a 2d5, not possible to have a 3f2. Number E, which of the following sets of quantum number are not allowed? For each incorrect set, state why it is incorrect. Starting for the first one, n is equal to 3, n is equal to 3. It's not possible, it is incorrect, because when you have n is equal to 3, you cannot have n is equal to 3. You can have either n is equal to 0, 1, and 2, because n varies from 0 to n minus 1. This is not allowed. N cannot have a value equals to L. For the second one, n is equal to 3. Yes, for n is equal to 3, it is possible to have n is equal to. For n is equal to 4, it's possible to have n is equal to 3. M is equal to 2, it's also possible because L varies from M varies from minus L to plus L. So, meaning that this is also possible to have M is equal to 2. Because for L is equal to 3, M is equal to minus 3, minus 2, 0, minus 1, 1 and 2, and 3. So it means that M is also included in this set. S can be either minus 1/2 or plus 1/2. Means that this one is allowed. Going to the third one, n is equal to 2, L is equal to 1. Yes, it's possible to have L is equal to 1 when n is equal to 2. M is equal to 1. Yet it's also possible to have M is equal to 1 when L is equal to 1. S is equal plus 1/2. It's also possible. So this is also is allowed. Then for the fourth one, n is equal to 2. L is equal to 1. Yes, it's possible to have L is equal to 1 when n is equal to 2. M, it's possible to have M is equal to minus 1 when L is equal to 1. But it is not possible to have S is equal to minus 1. S is always either plus 1/2 or minus 1/2. So this is not allowed. For the last one, n is equal to 2, L is equal to minus 1. So for n, L cannot be equal to minus 1. L cannot be a negative number. So L varies from 0 to n minus 1. So there is no way you can have L is equal to minus 1. Then this is not allowed. For F, how many total orbitals are there in n is equal to 4? Then they're asking to explain. How many total orbitals are there in n is equal to 4? N is equal to 4. So L can vary from 1, 2, and 3. Then for L is equal to 0, we have M is equal to 0. In that case, M is equal to 0, we have only one orbital. We have 4s orbital, which is one orbital. Meaning that for L is equal to 0, we have one orbital. We determine also the number of orbital for L is equal to 1. For L is equal to 1, M is equal to minus 1, 0, and 1. We have 3 orbitals. So 4p orbitals. Then for n is equal to 2, how many orbitals do we have? We have n is equal to 2. Have L. For L is equal to 2, we have m is equal to minus 2, minus 1, 0, 1, and 2. We have 5 orbitals. Then for L is equal to 3, we have m is equal to minus 3, minus 2, minus 1, 0, 1, 2, and 3. In that case, we have 7 orbitals. So when you add them together, we have 1 from L is equal to 0. We have 3 orbitals from L is equal to 1. We have 5 orbital from L is equal to 2. And we have 7 orbital from L is equal to 3. So when you add them, then you have 16 orbitals, 16 total orbitals. G is asking, write a designation for orbitals with the following quantum numbers. N is equal to 3, L is equal to 0. So when n is equal to 3, L is equal to 0, to find m will be also m will be equal to 0. In that case, you have 3s orbital. S orbital with n is equal to 3. In this case, you have 3s. For L is equal to 2, n is equal to 5, n is equal to 5, L is equal to 2. We determine the value of m. M will be equal to minus 2, minus 1, 0, 1, and 2. So how many orbitals do we have? 5 orbitals. This is the one which has 5 orbital. But because n is equal to 5, we have 5d orbital.